Hello, welcome to Troubleshooting, Advanced Debugging, and Error Handling. In the previous section, we explored concurrency and asynchronous programming. In this section, we're going to learn about the LLDB Debugger, enhancing breakpoints with conditions and actions, the LLDB command language, address sanitization, assertions, and also error handling. Now, we'll move on to the first video of this section that introduces the LLDB Debugger. In this video, we're going to take a look at breakpoints in the Breakpoint Navigator, the variable pane, and the LLDB prompt window. It's been said that about 50% of a developer's time while building an application is spent debugging it. If you've ever built an application, then you know this is pretty much an accurate statement. Whether you plan to work for an employer or for yourself, efficiency is important. If half of your time is spent debugging, you'd better become familiar with all of the tools available to you to aid in your debugging efforts. One of the first debugging tools that we become familiar with is to simply log values at different parts of our application to Xcode's console window. This simple technique can yield a lot of information about the state of the running application, which can be helpful in troubleshooting issues in our code. Of course, there's limitations to debugging exclusively with print or nslog. So let's become familiar with the LLDB debugger. Let's open our Game of Life application and open up the life.swift class. Once there, let's go ahead and add a breakpoint in our code inside of our evolve method. Breakpoints allow us to set places in our code where we want the control of our program's execution to be turned over to the LLDB debugger. After the debugger is taken over, we can view the variables in scope, examine the processes on each active thread, and even enter debugger commands that allow us to examine and even modify the state of our application. If we build and run our application, it should immediately break on the line that we specified. A few things happen when our application hits a breakpoint. Our Debug Navigator is presented on the left, which shows which thread our application stopped on. We can then view the different processes on each thread by selecting a given item in the thread's hierarchy. We also see that the LLDB console has opened up at the bottom in split view. The variable pane on the left has populated with all of the variables that are currently in scope. On the right, we see the LLDB prompt window, which allows us to enter commands for LLDB to run. In the left pane, we notice the letter A and the letter L next to our variable names. The letter A represents variables passed into a function as an argument, while the letter L represents a local variable. To the left of each variable, we see a disclosure triangle that allows us to expand the node to see the child variables within. For example, we've broken out a filter function that filters out our cells array, looking for cells with the current state of living. If we expand our self node, we'll see our cells variables within. Notice that it has 400 values inside of it. If we expand our cells node, we can examine each and every array item within. We can expand any one of the given elements in the array to see both the cell X chord, Y chord, and the cell's current state. Once our program has hit a breakpoint, we can step through our application line by line by using the LLDB transport ribbon. Starting from the left, the transport ribbon allows us to continue program execution, which tells our program to continue execution until another breakpoint is hit. Since we've broken on filter, which we know to be a loop under the hood, clicking continue will step us through each item in the array. Next is the Step Over button, which tells the application to jump to the next line of code. This button stops the debugger from following deep into methods that may not be helpful to debugging our current issue, such as framework-level code or even assembly code. Then there's the Step Into button, which tells our application that you do actually want to step into each method to explore every line of that function and each subsequent function involved in our program's execution. Of course, if the next step is not a function, our application just jumps to the next line. Finally, there's the Step Out button, which is helpful after you've stepped into your application a few times and you begin stepping into code that's not relevant to your problem anymore. Clicking Step Out allows us to jump back out into the place in our code where we initially set our breakpoint. On the right side of the LLDB ribbon, we can view the hierarchy of our code. More specifically, it shows us which thread we are currently paused in. Right now, it shows that we've paused execution in our life class on a function named evolve, which is running on thread 1. If we click on the execution hierarchy, we see a stack view that displays all of the code resulting from the method where we placed our current breakpoint. Notice that the method we broke on is numbered with a 0 in the call stack. If we click on number 1, we'll be taken to the previous method in our application, meaning the method that actually called our evolve method. We can click on each item all the way up the stack back to the beginning of our application's life cycle. In this video, we introduced the LLDB Debugger,